Hello everyone, and welcome to today's webinar in the CERDP and ESTCP webinar series. My name is Rula Deep. I'm a principal at Geosyntac Consultants in Oakland, California, and a coordinator of the webinar series on behalf of CERDP and ESTCP. I will be facilitating today's class. The webinar will consist of a brief overview of CERDP and ESTCP by Dr. Andrea Leeson, followed by a listing of the upcoming webinars in the webinar series. Following Andrea's opening remarks, we will transition to the technical portion of the webinar. Today's webinar features two speakers who will discuss new tools for characterizing and remediating munitions and energetics at military ranges. First, Dr. Tom Jenkins will discuss representative sampling and analysis for energetic residues in soil. He will be followed by a brief Q&A session. Second, Dr. Paul Hatzinger from CB&I will discuss bioremediation of commingled perchlorate and explosives in groundwater at an active military range. He will be followed by a second brief Q&A session, and we will conclude the webinar with an interactive Q&A session, including both of our speakers. Today's broadcast will be listen only. You may submit your questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we do encourage you to submit your questions in advance of that session. With over 200 people on today's call, it is logistically challenging to open all the lines for oral questions. Therefore, please remember that your phone lines will be in listen-only mode throughout this presentation. Here we've provided you with a few suggestions in case you experience difficulties with the broadcast audio. Typically, any delays will be fixed if you refresh your screen, and if that doesn't work, we do encourage you to use your conference line and to call in using that number provided on your screen. If you continue to have problems, please submit a chat in the lower left-hand chat box, and we will respond to your concerns accordingly. With that, I would like to introduce Dr. Andrea Leeson, who is the Deputy Director of CERDP and ESTCP, as well as the Program Manager for Environmental Restoration. Andrea has been with the CERDP and ESTCP program since 2001. Previously, she was a research scientist at Battelle Memorial Institute, where she conducted research on in-situ bioremediation. With that, I turn it over to you, Andrea.
Thank you, Rula. I'm happy to welcome everyone to CERDP and ESTCP's webinar today. CERDP is the Strategic Environmental Research and Development Program, and we were established in 1991 by Congress as a partnership between the DoD, the Department of Energy, and the EPA. CERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. CERDP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under CERDP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. CERDP and ESTCP are complementary programs with much of CERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are 4 program areas in CERDP, 5 in ESTCP. The Energy and Water Program area is only in ESTCP, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Climate Change, and Weapons System and Platforms, are CERDP and ESTCP programs that are managed jointly by a designated program manager. Our webinar today is focusing on research and demonstrations that were conducted under the Environmental Restoration Program area. Environmental restoration has essentially 5 main areas of research: contaminated groundwater, contaminants on DoD testing and training ranges, contaminated sediments, wastewater treatment, and risk assessment. Under the environmental restoration area, I just want to make you aware of a recently released special solicitation that's focused on post-remediation performance assessment. The solicitation was released on May 11th, and proposals are due on June 11th at 2 p.m. We held a webinar last week that provided an overview of the solicitation, and this webinar has been archived on the CERDP and ESTCP website. Please refer to this solicitation link on the slide to get full information on this particular solicitation. Our webinar series will be highlighting research and demonstration efforts from each of the 5 different program areas. And as you can see, our webinars will cover a very broad range of topics, with upcoming topics covering colored smoke and flares, to remote methods for water conservation, to emerging contaminants. The next webinar based on research and demonstrations under the Environmental Restoration Program area will be held on August 20th and will cover characterization and remediation in fractured rock environments. You can find more information about upcoming webinars on the CERDP and ESTCP website listed here. And at this point, I hope you enjoy the webinar today. Rula?
Thank you, and it is now my pleasure to introduce Dr. Tom Jenkins. Tom is a private consultant after retiring from the U.S. Army Corps of Engineers. He was with the Engineer and Development Center for 37 years, where his research was directed at developing analytical methods for determining the concentrations of explosives and related chemicals in the environment. He also conducted research targeting the detection of buried landmines using chemical detection methodologies. His achievements include the development of standardized laboratory methods for the determination of nitroaromatic, nitramine, and organonitrate explosives in soil and groundwater. Dr. Jenkins has published over 60 journal articles and over 100 government reports, and he has presented at numerous professional symposia. Tom, we're very happy to have you here. Please go ahead and get started.
Thank you, Rula, and I appreciate all of the folks who are calling in today. I've been away from the field a little while, so it's very nice to know that people still remember something about what I've done. Anyway, today, as Rula said, I'll be talking about representative sampling and analysis for energetic residues in soil at military training ranges. Now, I'll be presenting today, but the work was done by a number of individuals, both in the ERDC, that's the Engineering Research and Development Center, Envirostat, it's a company that Chuck Ramsey is the principal in, and our colleagues from Canada at the Defense R&D Canada, Valcartier. In particular, folks at the ERDC, Marianne Walsh, Alan Hewitt, Michael Walsh, Susan Taylor, were very instrumental in much of the work that I'll be presenting. And the work on multi-increment sampling was coordinated and shared with that of Chuck Ramsey. The overview of the presentation today, I'll start with a very brief discussion of residue deposition. Really, the idea here is in order to figure out how you must sample for something, you need to understand how it was deposited. We'll be talking more extensively about range sampling, how to develop a means of collecting representative soil samples to determine whether there is a contaminant issue or not. And then briefly we'll talk about sample processing so that if you get a representative sample coming into the laboratory, you don't lose that representativeness as you're processing and subsampling the sampling. Before this work was done, much of the work on ranges was done by the traditional grid node sampling approach. And in this case, basically the site was divided into a number of sampling units. One or a couple of discrete or grabbed soil samples were collected to represent each unit. And then they were subsampled in the lab using a grabbed sampling approach. Analytical results from the discrete samples were assumed to be normally distributed and representative, although there was really never enough data to know whether they were or not. And the mean or 95% confidence limits were established using a normal statistics. But the question is, were any of these assumptions correct for energetic residues? And when I'm talking about energetic compounds, I'm talking about nitroaromatics such as TNT, nitramines like RDX, and nitrate esters such as nitroglycerin. We conducted field sampling experiments over 32 ranges in the U.S. and Canada, basically from coast to coast, including Alaska and Hawaii. The residue deposition studies were designed to provide information on the nature of the residue deposition. We used pans to collect residues for microscopic inspection. That was done largely by Susan Taylor. And we conducted studies at snow-covered training ranges to allow estimation of mass deposited. And that work was coordinated mainly by Michael Walsh and Marianne Walsh. These are some microscopic photos of some of the residues that were deposited both at firing points. This would be the two on the left. The fiber is a fiber from a 105 millimeter howitzer firing. It was a nitrocellulose fiber that contained about 24 micrograms of 2,4-DNT. You note on the lower right, this is a round that had undergone a low order detonation, and that's one in which the round only partially detonates, and you can see the chunks of TNT lying next to the round there. I won't get into the details of this work except to talk about the conclusions. Basically, at firing points, the residues are fibers and particles of nitrocellulose imbibed with either nitroglycerin or 2,4-DNT, depending on what type of propellant was being used in that particular weapon. At the impact areas, residues are particles from low-order detonations and ruptured rounds, and most remain at the soil surface. High-order detonations produce only very, very small amounts of residue, whereas one low-order detonation can produce as much residue as 10,000 to 100,000 high-order detonations. So for most sampling ranges, these materials are raining down from the sky and land on the surface and remain there. And so a sampling depth of about 5 centimeters is recommended, including deeper soil. It doesn't change the mass present, but it does dilute the concentrations and make it sometimes more difficult to detect what's present. So why in the world would we be interested in sampling at military ranges? Well, the major potential problem is migration of energetic compounds off-range in aqueous solution. And this is mostly a concern in groundwater, not so much in surface waters. Ecological risk assessments such as that at Eagle River Flats, where Fort Richardson's impact area was closed because of waterfowl poisoning with white phosphorus. There wasn't DOD established a directive 4715.11 that required each DOD component to assess environmental impacts of munitions, and sometimes that's going to require sampling to establish residue concentrations. And the MMRP program does do sampling under the DIRT program for formerly used sites. So when we sample, what is it that we really want to know? We want to know is the mass of energetic residue in the sampling unit sufficient to present an unacceptable risk. And this is estimated from the mean concentration in the source zone. The other question is the mean concentration present in the sampling unit soils above some risk criteria for target organisms. So in general, what we really want to do is get an estimate of the mean concentration with some level, good level of certainty. I'm going to be talking about a number of experiments that we conducted that were conducted in a similar manner. So I'm going to talk about this. This was a 10 by 10 meter sampling unit at Holloman Air Force Base. And we divided that 10 by 10 meter sampling unit into 100 1 by 1 meter grids and collected a discrete sample from each of these 100 grids. Now, normally using the old approach, any of these would have been a legitimate sample under the grid node sampling approach to characterize this range. But as you can see, the concentrations go from 0.2 to 778 within this 10 by 10 meter area. So taking a discrete sample would be a very poor way to estimate the mean concentration. Now, even if you take a look at one of these grids, for example, how well does that number represent that 1 by 1 meter grid? Well, we subdivided a 1 by 1 meter grid into 9 discrete areas, 1 foot by 1 foot, and collected discrete samples in all of those areas. And ignore the range on the right part of the slide. It's incorrect. But you can see the numbers here vary from even within this 1 meter unit over several orders of magnitude. Now, the fact that these differ is not due to analytical error. We could reproduce these numbers within a very close level if we did duplicate analysis. So this is not an analytical problem. This is a sampling problem. This is another area we sampled. This was at Fort Polk. It was in a RDX contaminated area, artillery mortar impact range. You see the concentrations here vary from near zero to over 2,400, about 2,400 milligrams per kilogram. And that's all within a 10 by 10 meter area. So you can see it's not easy to collect a discrete sample that's going to represent the mean concentration in an area such as this. Now, we did this experiment in a number of different places, both in firing points like we did at Donnelly Training Area and Canadian Force Base Cartier, and impact areas, 5 impact areas. The type of range is listed, the major analyte present in these areas, the range of concentrations found within those discrete samples. We did these 100 discrete samples in each one of these areas. You can see the concentrations vary widely in all cases. You can see the mean and the median do not agree. In other words, most of the concentrations are lower than the mean. So if you just take one or a few samples, you're likely going to underestimate the mean. And none of these distributions were normal. They were all skewed. Conclusions from these sampling areas from these sampling studies, using discrete samples. The distribution of explosive residue is spatially very heterogeneous, even over short ranges, at all types of military ranges. The distribution of discrete samples is always non-normal. So if you take your data and you use normal statistics, you're just kidding yourself because they're not legitimate when you're using discrete sampling. Sampling error using discrete samples at least 10 times the total analytical error, and that includes subsampling. So the major thing that you have to do if you want an estimate of the mean is collect a good sample. So sampling area was reduced using some form of composite sampling, and you cannot obtain representative soil samples using one or even a few discrete samples. Okay, so if we can't use discrete samples to do this, or grad samples, what other types of approaches might there be? And as I mentioned, some form of compositing really does help. And one of the methods that we spent quite a bit of time investigating was multi-increment sampling. Now, this term was devised by Chuck Ramsey, who's a registered trademark of Environmental Stat Corporation. So some people use ISM, or the incremental sampling method, instead of MIS. But in either case, we're talking about the same thing. Basically, by combining individual increments of soil from within the sampling unit to produce a single sample. This is typically used to get a more reliable estimate of the mean, and reduces analytical cost by reducing the number of samples actually analyzed. And as you'll see, it normalizes the data. Now, these are some of the composite sampling approaches that have been tested. The 5 increment sampling box was used by some organizations, but reproducing the results using this approach were very poor. The 7 increment sampling wheel was something I devised to just look at the short range heterogeneity. It was never envisioned as an approach to composite sampling. And then the multi-increment sampling design that I'm going to talk much more about. Basically, you can think of this as like our 10 by 10 meter area, for example. And as we walk back and forth systematically across the site, every place where there's an X, we might pick up an increment of soil and put in our bag. And we keep doing that, and then the red one would be if we collect a duplicate sample across the site. So in this case, we collected 100 increments. In this particular design, I show 100 increments being collected. The sampling tools that are useful for MIS sampling, the one that's the most useful is the one with the red handle, red bar here. This is a multi-increment sampling tool devised by Michael Walsh at Krell. And the advantage of this approach, it's like they call it a pogo stick sampling. You can walk very quickly and put this into the ground and produce a little core right here. This little core, you can see the depth and the diameter very well characterized. And so you can get a very quick way of collecting a multi-increment sample using that tool. This is a Fort Lewis anti-tank rocket range where Diane Root at Concurrent Technologies compared discrete samples, the box sample, the wheel sample, and multi-increment samples. This was in a firing point sample, so we're talking about propellant residues. You can see the difference, the range in values, very high for discrete, very high for the box, very high for the wheel, but the range of samples results collected or determined for the MIS samples is much smaller. The relative standard deviation only 9% for the multi-increment sampling approach. Holloman, at the Holloman bombing range, this was also conducted by Diane Root at Concurrent Technologies. The same experiment with discrete box, wheel, and MIS samples were conducted. You can see the same results. In this case, it was TNT, and much reduced RSD for the multi-increment sample. This is some examples of some of the results that we obtained when we used the same 10 by 10 meter area where I showed you we collected the discrete samples. We also collected multi-increment samples. We did the 100 discrete samples. The values varied over 4 orders of magnitude, whereas the values among 10 multi-increment samples only varied by a factor of 2. The distribution for the discrete samples was skewed, as always, and the normal distribution was adequate to describe the distribution of the 10 multi-increment samples. You can think of why does this work so well. You can think of it, this is how I've written the central limit theorem applied to multi-increment sampling. As the number of individual increments within each sample gets large enough, the distribution in replicate samples can be approximated by a normal distribution, regardless of the shape of the distribution in individual increments are, as you remember, discrete samples. So what's large enough? In most cases, you have to have at least 30 increments for this to work. So here's some examples of places where we use multi-increment sampling. This was at Holloman Air Force Base bombing range. We collected 3 multi-increment, 100 increment samples within a 10 meter by 10 meter area. The minimum concentration, 12.5, the maximum, 17.2. So it was very easy to, we did a very good job of reproducing these using the 3 multi-increment samples. This is another area. It was a 20 by 20 meter area that Marianne Walsh collected in Alaska. Collected 200 discrete samples. Most of them were less than the analytical detection limit, so that the median value for discrete samples is a less than value, whereas the maximum was 4,450. So we're talking 4 or 5 orders of magnitude difference from individual discrete samples, and the minimum to maximum is only about a factor of 10 from the multi-increment samples. In this case, the distribution of the multi-increment sample was not normal; it was also skewed. These are values. These are also results from collecting multi-increment samples within 10 by 10 and 100 by 100 meter sampling units at various ranges. You can see we went at firing points and impact areas. all kinds of different types of ranges, the number of increments in the sample, the number of replicate samples collected. You can see in almost all cases the results were a normal distribution, a very small range between increments. In the one case, we did have a fairly large difference for Ford Polk, and this was before we used the systematic random design where we collected evenly across the site. This was a totally random design, and we may have oversampled or undersampled various parts of that range because of that. So let's compare what we found with discrete versus multi-increment samples. There's a very large range in data from discrete samples, much smaller range for replicates of multi-increment samples. Distribution of discrete samples, always non-normal. Distribution of multi-increment samples often is normal. The median for discrete samples always less than the mean, thus most discrete samples underestimate the mean. Generally, the median and mean concentrations are quite similar for multi-increment samples, and the use of multi-increment samples almost always eliminates the problem of dealing with less than data, which is always a challenge. So the recommendation is to collect replicate 30-plus increment samples to represent the sampling unit. Now, once you have the sample, you're sending it to the lab. With the multi-increment sampling approach, you have a kilogram or more of the material. So what happens when it gets to the lab? Well, you have to remember that subsampling issues are just a miniature of the field sampling issues, and they're dominated by heterogeneity within the jar or bag. So processing and subsampling is the second largest source of characterization error. So if you're not careful, you can lose the representativeness gained using the multi-increment sample. Current laboratory QA often ignores a lot of these subsampling issues and concentrates mostly on the determinant step, the instrumental analysis. Now remember, when we're bringing back these samples to the laboratory, what's present in these samples is a lot of soil and a few particles of explosive from impact areas or propellants from firing points. So if you want to think, you need to think about this a little bit. Just as an example, let's go through this calculation. If your sample is residues of composition B, when we did microscopic analysis, we found out that these particles were in size ranges between a few millimeters and centimeters. Well, soil-sized particles are defined as less than 2 millimeters. So if we have one millimeter spherical particle of composition B, it weighs about 0.9 milligrams. About 0.5 milligrams of that is RDX. So if the soil concentration in your bag is only 1 milligram per kilogram, you have only 2 of these particles. So therefore, there's no way you're going to reach in your bag and get a grab sample in which you're going to get the correct result. You've got to grind the soil to a fine particle so you can break up these particles of propellant or explosive so that you have a hope of getting a representative sample. This is a study that Marianne Walsh conducted some time ago where a very uniform-looking soil sample was collected from a hand grenade range, and Marianne took 12 subsamples of this that were not ground. And the TNT concentration and the RDX concentration for the not ground is shown here. And you can see the values vary quite a bit with the RSD for the TNT of 143%, and that for the RDX of about 99%. When these samples were ground using the puck mill grinder, you can see that the results for individual subsamples were much closer, and that the relative standard deviation was reduced to only 2.57% for TNT and 1.23% for RDX. Thus, you must grind these samples to a fine particle size in order to enable collection of a representative subsample. Otherwise, you'll destroy the representativeness of the sample as you collect it in the field when you're doing the processing in the lab. So the conclusions from the sample processing experiments, which I really don't have a lot of time to talk about today, the entire sample must be processed. There's no grab sampling, no scoop off the top allowed. The soil sampling is first air dry and then ground using a puck mill grinder. Other grinders have been evaluated, such as roller mill, coffee grinder, and others, and they've been found to be ineffective. Much less, the standard deviations are much higher using these other types of grinders. So this subsampling approach has been incorporated into SW 846 method 8330B, as well as an appendix that talks about the multi-increment sampling approach. So our recommended approach for site characterization, develop a sampling plan that is a proper stratification of the sampling units, collect representative samples from each sampling unit using multi-increment sampling, grind the soil that's sent to the lab with a puck mill grinder to obtain representative subsamples, and determine when you have a subsample for extraction and analysis, determine that using HPLC UV or HPLC MS or MS. Just remember, however, that the analysis, the actual instrumental analysis, contributes the lowest portion of the random error, but almost always receives by far the largest QA/QC attention. We need to spend much more of our QA/QC attention on sampling than subsampling. So the conclusions of this work: a major portion of residues of impact areas result from low-order detonations. Remember, it takes 10,000 to 100,000 high-order detonations. And that high-order detonation is one in which the round detonates as designed to produce the residues from one low-order detonation. Energetic residues are deposited as particles non-uniformly across the sampling units at both firing points and impact areas. Discrete samples are not useful for characterization because of the non-uniform distribution of residues. Multi-increment sampling, or ISM, produces an adequate approach to reliably estimate the mean concentration. And samples must be ground in the laboratory using a puck mill to enable reliable subsampling. Some additional places to obtain information about these studies for the various projects can be found here. There is additional information available in the EPA Federal Forum issue paper on multi-increment sampling, and the ITRC has issued a guidance document on multi-increment sampling. So with that, Rula, I guess we'd be open for questions.
Yes, thank you, Tom, for a very informative presentation. I would like to remind our audience to submit questions by using the chat box on the left-hand portion of the screen. Tom, we've received a number of questions, and I'm going to start posing them to you. EPA often receives contractor work plans that propose a low 1 to 7 discrete or ISM increment samples. Your studies show that this is not sufficient to meet precision goals. Is that correct?
Yes, if you don't use at least 30 increments within your multi-increment sampling, the whole concept of developing a sample that's a part of a normal distribution and it is not going to work, just not enough increments to reliably produce a sample that you can use to develop an average concentration. Remember, that's what we're trying to estimate is the mean concentration. Using only a 7 increment sample, you're not going to get a good estimate of the mean.
Thank you, Tom. Can you please let us know if the regulatory community has accepted your proposed approach?
Yes. The EPA, as I mentioned, the EPA Federal Forum issue paper on multi-increment sample was issued a couple years ago. It's included, the MIS sampling approach is included in the analytical method, SW846 method 8330B, and the appendix of that method is a step-by-step approach to using the MIS approach. So the EPA is very favorable, has shown very favorable comments on this method. And some states require the use of multi-increment sampling now. So, yes, I think the regulatory community is on board with this.
This is very promising. Thank you. Can you please discuss any safety issues associated with grinding these samples in a ring and puck mill?
Yes, this has been voiced as a concern in the past. When we do this, we air dry the soil first, and we sieve it to make sure there's no pieces larger. I forget the exact number of the sieve. It's given in the appendix of the method. And if the particle size is below that size, it cannot initiate a detonation. So we feel quite confident. We've ground thousands of samples now, never had any kind of an issue, and no one else that I know of who has been using this approach has had any issues with that at all.
Thank you. Does the degree of grinding depend on the nature of the energetic residue?
Yes, it does actually. The residues from firing points that are made up of nitrocellulose, that material is often, you can also think of it like wood, and it takes additional grinding to get that to the particle size of interest, which is like a talcum powder actually when it's done. It's less time consuming to do that for crystalline materials like explosives like RDX, TNT, composition B. And the amount of time that's required for these various types of samples is given in that appendix in SW 846, method 8330B. But it's a little bit longer for the propellant residues than it is for the explosive residues.
Thank you, Tom. Are you aware of any examples where your sampling strategy has been used for other types of contaminants like arsenic in soil?
Well, Jay Clausen at Corel has done a lot of work on heavy metals, and metals are often distributed in the same way as particulates. So, and I think there's been work with residues of uranium and other things from DOE sites, and in all of those cases where the residues are deposited as particles, this approach works very well.
Great. And can you tell us why energetics in surface water are not as much of a concern as groundwater?
Well, there's a huge dilution that occurs with a running stream, and sometimes that's much less of a concern in groundwater. The groundwater aquifers can be quite narrow, so I think it's largely a difference in dilution.
Great. And for the bombing ranges, what era were the munitions? Are there any World War II sites?
I did not, let's see. We did not sample as a part of this approach an older sampling site like that. I'm sure that the MMRP program has done so, and some of the National Guard sites, they're doing some of these old ranges. But as a part of our R&D, I don't remember us doing an older site like that.
Thank you. And one last question. Everyone keep the questions coming. We'll have another Q&A session that Tom will participate in towards the end. But one last question before we go to Paul. Can you elaborate on how the ISM approach can be adapted for evaluating metals in soil and comparing metals concentrations to background soil conditions?
Well, again, the multi-increment sampling approach is quite relevant for metals. Again, the distribution, the contamination occurs as particulates landing on the soil surface, and they don't migrate. The source remains at the surface, so MIS is a very good approach for collection of representative samples in a sampling unit. And in the same situation as with energetics, the sample must be ground to find sort of a particulate level. And when that's done, the representative soil samples that are then collected, subsampling, are quite good. You do need to do the same sort of thing in background areas so that you have an idea of what the background level is for these samples. And in particular, using multi-increment samples, you get a more reliable estimate of what the background is as well. So with the standard deviations being reduced for both the background and the potentially contaminated site, you will be much more able to tell whether there's been an impact from metals in the sampling unit of interest.
Wonderful. Thank you so much, Tom. And it's now time to transition to our second speaker, who's Dr. Paul Hatzinger. Paul is the Director of the Biotechnology Development and Applications Group of CB&I Federal Services. He holds a PhD from Cornell University and has more than 20 years of experience in the biodegradation of contaminants, bioremediation applications, microbial ecology, stable isotope analyses, and groundwater microbiology. Dr. Hatzinger's research group has been instrumental in the development and field application of new remedial approaches for several contaminants of concern to the Department of Defense. These include perchlorate, MTBE, nitramine, and nitroaromatic explosives. In addition to his research, Dr. Hatzinger does extensive consulting on the sources, fate, and remediation of organic and inorganic pollutants. And with that, I turn it over to you, Paul.
Great. Thanks, Rula. So today's topic is going to be the results of an ESTCP project, 201028, where we were evaluating the bioremediation of commingled perchlorate and explosives in groundwater at an active range. So on the agenda, the key question we were really trying to address here is, how can typical DoD range contamination in groundwater be treated? We'll start out with a little background about the types of contamination you see, although Tom did a very nice job there, our objectives and technical approach, the demonstration site that we worked at. We'll go through some of the key results, as well as some supporting stable isotope data through a new method developed to look at stable isotope fractionation of carbon and nitrogen in RDX, and then finish up with some overall conclusions and recommendations. So a little background, as Tom showed, you do get, with low order detonations, you do get residues of explosives as well as perchlorate on typical ranges. It's very common to find these as both particulates in soil and dissolved in groundwater. And it's important to note that sustainability of ranges really depends on preventing off-site migration of these contaminants. But you want to also use technologies that aren't going to impact the DoD testing and training activities. So studies, and quite a few of these studies were actually funded dating back to probably the late 90s through the early 2000s on degradation of perchlorate and nitramines. But essentially, these laboratory studies have shown that they're both readily biodegradable under anoxic conditions, and that occurs when appropriate carbon substrates are supplied. So if we look at the graphic on the lower left, this is our perchlorate-reducing bacterium. And essentially, we provide these organisms with a substrate, which we also call an electron donor. It's a carbon source typically. Things like acetate and lactate, different fatty acids work well, sugars, molasses, cheese whey. There's lots of different potential options here. So these organisms grow on these substrates and convert themselves into more organisms or biomass in CO2, and they break down perchlorate during the process. And the perchlorate, the ClO4- is broken down through chlorate and chlorite through a known enzyme called perchlorate reductase. Then that chlorite, which is fairly toxic, is broken down further to chloride and water. So we understand this process very well. On the other side of the slide, we see RDX biodegradation. Obviously, this is a much more complex molecule. There's also multiple pathways for its degradation. One of the first pathways along the top portion of this graphic shows a reduction of the nitro group in red to a nitroso group. And this happens at all the nitro groups in RDX. You get these molecules called DNX and TNX. And ultimately, you get a cleavage of the ring to form small molecules like formaldehyde and methanol, which are readily utilized by other bacteria in the soil. There's also a pathway where you can get a very early ring cleavage through something called methylene dinitramine or MEDINA. And again, that'll break down further to things like carbon dioxide and nitrous oxide. And I should say that, in the literature, there's a lot of studies that show there are some cultures that can aerobically degrade RDX and the other nitramine HMX. But this is not very commonly documented in the field. Rather, these things tend to degrade under anaerobic conditions. So our main objective then was to validate the in situ application of an emulsified oil barrier or biobarrier. And this is for passive treatment of commingled perchlorate, RDX, and HMX at a range. We wanted to see if this approach would be effective. We wanted to see if we could implement it without affecting any mission critical activities. And we also developed and applied a stable isotope technique as kind of a supporting information to document RDX biodegradation in the field. So as a technical approach, one of the questions on a range is, how do you best apply a carbon source to meet range requirements? And as we noticed by the photo in the lower right, they do blow things up on these ranges. So you really don't want to have a surface footprint. You don't want vulnerable system components. You don't want any type of ex situ system or a bioreactor where you're pumping groundwater. You want a short installation time because many of these ranges are quite busy. You want to be minimally invasive in the subsurface because, of course, you typically need UXO clearance for any wells that you install or any types of systems you install. You want something with no power as well as minimal O&M. So clearly a passive approach is really what you like to do here. And a slow release substrate makes a lot of sense, something that will slowly release carbon over a period of time and give you sort of long-term degradation of your contaminants of concern. So emulsified oil and emulsified oil barrier explicitly meets a lot of these requirements. Now, emulsified oil products were developed, dating back, I think the first patent on this was 2002. By Bob Borden, and essentially what we have here is we have a soybean oil that's sort of diluted up, and there are other nutrients added. There are surfactant agents added. It forms kind of very small particles, and when you're working with this in the field, it looks a lot like skim milk, as we see in the photo in the upper right. As you inject this oil into the subsurface, it binds to particles. You sort of flush typically with a little bit of chase water, and you can form a barrier where essentially you've got this oil that's attached to surface particles, and bacteria will slowly start to break down that oil, and as a consequence, these organisms, different types that can grow on this oil, can also degrade your perchlorate or RDX. In ideal situations, these barriers can last potentially up to 5 years. That depends a lot on the concentration you use, the water chemistry, and what other electron acceptors are there. Things like sulfate can provide a large demand, or oxygen in some instances, and of course the hydrogeology, the groundwater flow. But this is a nice choice for a barrier on a range. So our demonstration site was the Churchill Range at the Naval Surface Warfare Center, Dahlgren, Virginia. This is about 40 miles south of Washington. It's a range that was actually opened in 1918. The facility was opened in 1918. And this Churchill Range is part of a larger complex called the Explosives Experimental Area, which covers about 16 acres. It's bordered by the Potomac River on one side and Mahotic Creek on one side, so there is access of to water bodies. So what they do here is they test a lot of experimental formations. I think officially their charge is research, development, testing, and evaluation of explosives. But they work with a lot of different types of explosives. They're extremely busy, so they're working most weekdays. So it's very hard to get on and off the site for extended periods of time. You have to do your work in a day or two typically, so they can continue their activities. In terms of the aquifer, this is a shallow perch groundwater aquifer. It's not an ideal situation really for injecting anything. I just put up one of our borehole logs, and basically what that shows is you hit a clay layer at about 10 to 12 feet below ground surface, and that clay layer, I think we drilled down to 30 feet and never got through it. So the nice thing is that it's shallow. All of your contaminated water is perched above this clay layer. There was no contamination found down in the clays. But most of your movement is through these very small sand stringers or small sand gravelly areas. So that's where most of your RDX and perchlorate is sort of moving through this groundwater environment. If you look at the core in the lower right, on the right-hand side of that, you can see this pure gray clay. And just above that, you'll see some of the sandy gravelly layers that you hit in the aquifer. The other challenge here is that the aquifer tends to be low pH, averaging between 4 and 5. And this can be an issue for degradation of contaminants, many types of contaminants. As you get down to low pH, degradation rates slow or they don't degrade at all. Perchlorate is one of these. Once you get at a pH below the low 5s, you find that perchlorate biodegradation tends to be impeded. You need to buffer the aquifer up a bit from that range. So as Tom showed, you tend to get these explosives in soils, and there are explosives in lots of different areas across this range. And you don't also get sort of normal plume maps like we're used to seeing for things like TCE or PCE, where you have a source area and then you have an increasingly dilute plume that's sort of moving away from that source area. And a real nice example is in the upper right. And we ended up putting in a large number of borings at this site. There were only a couple of wells when we started. And essentially what you see here by the contours is there appears to be sort of two, we'll sort of call these plumes, but what you tend to have is you have sort of a couple areas where you have very concentrated RDX, and those concentrations go up to about 100 to 150 ppb, which would be fairly typical in groundwater. You don't tend to get high ppm concentrations. This would be fairly typical for many sites. But interestingly, groundwater flow is to the southeast, as we see by the arrow. But you see you have lower concentrations to the northwest, and you have lower concentrations, as you might expect, to the southeast. But the question is, well, why are these lower concentrations occurring above these source areas? And I think the answer to that is what we're really looking at here is potentially sections of plumes. And if we continued to go to the northeast, or the northwest rather, we might find other source areas, and these plumes are kind of moving into each other because we're dealing with chunks of explosives that have basically been dissolved into water. So for our demonstration, we chose an area. Some of this was based on geology as well as concentration, and it's sort of that little green bar line in the one plume, and we installed a pilot scale biobarrier. And this barrier is about 30 meters long, down to about 3 to 4 meters deep, so 10 to 12 feet. With UXO clearance, we put in 20 injection wells, which are the small blue points. They were spaced at about 1.5 meters. We also installed 16 monitoring wells, some of which were control wells that weren't expected to be impacted by the barrier, and other wells, sort of went down where we expected the groundwater flow through the barrier. Now, we added an average of about 250 liters of a 4% emulsified oil, and we used 0.75% of a magnesium hydroxide buffer. And some of this was just based upon laboratory testing. It took us about 3.5 days to install the barrier, and really most of that time, because of the geology here, was just injection time. We could only inject a lot of times at 0.1 to 0.2 GPM in these 20 wells, so it's just a very, very slow process. And while I'm on this slide, I'll also say that there was a former ESTCP project, which is ER0626, and that was some work that Bob Borden and others did. And they developed a very nice design tool. So if you're going out and you're going to be working with emulsified oil, they have a very simple design tool that you can put in some of your site hydrogeology, your contaminants, and you can come up with information that will give you both, some technical guidance in terms of what you inject, concentration-wise, as well as some, sort of some financial guidance, so what kind of cost you'll probably be looking at. So it's a really nice tool that's available to the larger community to use if you're putting in an emulsified oil barrier. So some results then, and what I'm going to show here is basically, if we look at the little graphic on the right, that's just a layout of our plot. And I'm going to show results from the wells kind of going right down the middle of that plot. So we'll start up. So if we're looking at the figure here on the left side, we're looking at a well that's 10 feet up gradient of the biobarrier. The dotted line represents where the biobarrier went in, and then as we move to the right, we're 10, 20, 30, 40, 50 feet down gradient of that barrier. So as we look, the barrier was installed in February of 2013. So our open diamonds show our pre-barrier sampling, and I'm only showing a portion of the data. There's more sampling events, but this kind of signifies the results from the project. So you can see when we started along the length of sort of all the wells, we had somewhere between about 25 and 40 ppb of perchlorate in groundwater. Once we get our injection, we start to look at June, which is the red boxes. Pretty much no change up gradient. Down gradient of the barrier, we're down to between 0.5 and 5 micrograms per liter. And the results I'm talking about are primarily within 20 feet of the barrier, because that's what we impacted sort of early on, and we expect sort of movement further down with time. By 8 months, we basically were below 1 ppb within 20 feet of the barrier within all the wells in terms of perchlorate. And then as we move further, as we get out 16 months, now we're looking at the blue squares, we can see we have some rebound. So we're starting to exhaust our biobarrier, and we used a fairly dilute concentration of emulsified oil in this case. But we're starting to see a rebound of perchlorate. So now results for RDX. Very similar actually. We see again we had about 80 to 160 ppb of RDX. And as we look at our red boxes in June, we had very nice degradation within, that's only 4 months after installation, so those organisms are there, they're degrading RDX. By 8 months, within 20 feet of the barrier, everything was between 0.01 and 6 ppb. And again, with the blue squares, we see that we're starting to get some rebound after about 16 months. HMX tends to degrade more slowly than RDX, and there's been a few studies which suggest that, in fact, it doesn't degrade until RDX is largely gone from environments. And that was also shown here. We had fairly low concentrations of HMX, 13 to 20 ppb to start with. We didn't see a lot of degradation in our first 4 months. That would be the red squares in June. However, by the time we hit October, or 8 months, we're down to just 0.3 to 2 ppb. So we then see pretty good degradation of HMX. And again, we start to see significant rebound after 16 months. The other thing that's interesting here, there's always some concern about buildup of degradation products of RDX, and in particular, MNX, DNX, and TNX, which are these nitroso derivatives. There's also some toxicity associated with these. And in this case, I added a few more sampling intervals here, but we see some production early on of MNX, and again, the red squares are 4 months. But then that falls away, and again, by about 8 months, the yellow triangles, that's pretty much gone. And if you look, we're only seeing about 6 to 8 ppb. So of the 80 to 160 ppb of RDX, we're really seeing only a fractional amount of this produced, which suggests that we're getting good ring cleavage of RDX anyway. The results are fairly similar, where we see some buildup of DNX, which again then decreases as we get good RDX degradation. And then finally TNX, and this was kind of interesting because we see this August time point, which was about 6 months after we installed the barrier. We get a pretty nice pulse of TNX. So it suggests that we're getting MNX going to DNX, going to TNX, which is what you would expect to see. But then again, that TNX also breaks down. So by October, we have very little of that remaining. So it just shows that we're getting a little bit of these degradation products, but they're degrading with time as well in the barrier, which is good to see. So our next slide, pH. Now again, this magnesium hydroxide product that we added was particulate, and it actually did a very nice job in moderating the pH. You can see we started at only pH of about 4.5 upgrading of the barrier, and certainly within the 20 feet where we had some early distribution of the oil, our pH values got between 5.5 and 6.5. And then even with time, after 16 months, we still had some elevated pH, which is nice. The other thing that we see is total organic carbon. Now remember, a lot of the oil is actually sorbed on particles. When you're sampling water, you don't see that. What you tend to see are fatty acids that are fermented from that oil. And you can see we had sort of low concentrations, never really anything upgradient. And then as we sort of saw our best activity, we had about 5 to 90 ppm of those in solution. And then that kind of falls off by the time we hit 16 months. Again, that's consistent with us exhausting our barrier over this period of time. So we had nice performance, and then we're starting to exhaust our TOC in the barrier. So just a quick summary then of performance. We met our remediation objectives. Our goal for barrier life was 2 years, but again, we specifically chose a fairly dilute oil, and part of the reason to do that is I was a bit concerned about, we really have these small areas, these sand stringers where a lot of the water flows, and I was a little afraid about using too high concentrations to begin with. The other issue here, and what we kind of see from the figure on the lower left, is that we get again, it's a shallow aquifer, but we get a lot of variation in the water table here with time. And the water table is anywhere from, basically at your ankle sometimes of the year, where we have almost no, the water's right at the top of the wells, to about 4 or 5 feet below surface. So when you install a barrier in an environment like this, you're going to have times of the year where the barrier is dewatered, and you're certainly getting oxygen intrusion, and I think you're going to get a lot more oil consumption when you have free oxygen flowing into these environments. So you have to consider that, and actually a recommendation, if this was going to be done full scale at the range, would be to go ahead and put in some type of trench barrier with some permeable materials. You'd have to, of course, do your UXO clearance, but that would be doable over the areas where there's discharge from the range. And then have some lines in there where you could periodically inject some more emulsified oil, and you could probably do that in half a day to sort of keep this technology, working over the long term. And I'll say that we did go out and we re-injected some points of the barrier. We added another 2,700 liters of a more concentrated, about an 8% emulsified oil and more buffer. And we're still in the process of evaluating the longevity of that and kind of the second phase of the approach here. So, those results will be in the final report, and we expect to do 2 more sampling rounds this year to finish this out. I'm going to wrap up with just talking a bit about stable isotope analysis and how that can be useful in documenting RDX biodegradation. So when you have something like RDX, we're just looking at the graphic on the right, a very small percentage of RDX just naturally occurs as N15 RDX. So this is a isotopically heavier RDX. And when bacteria break down lots of different contaminants, but including RDX, they degrade the lighter RDX, so the N14 RDX in blue, at a slightly faster rate. So if we go through time, we go from the top to the bottom graphic, we see that our RDX is degrading by, you can see that by the lower concentrations that are coming to the bacteria, but you're also seeing an enrichment in the 15N RDX. And this is something that can be documented. And it can be a very powerful tool to look at both sort of natural attenuation potentially of RDX, as well as to document degradation of RDX in a demonstration such as this. And so when we look at isotopic fractionation, and this was, let me just mention that this is a CERT-up project, and this was some work that is done by Neil Sturcio, who's now at the University of Delaware. He recently moved from University of Illinois at Chicago. And essentially what was done here is there were a variety of different strains growing up that were known to degrade RDX, and they were incubated with RDX, and then with time the concentrations were measured, and the stable isotope ratio of nitrogen and carbon and the remaining RDX was quantified by isotope ratio mass spectrometry. And if we look at the graph on the right, what we're really looking at there is sort of the natural log of the fraction of contaminant remaining. With -2 being about 90% of that contaminant degraded, against the stable isotope ratio on the left. And this is just, again, a natural log of sort of the ratio of N1514 in your parent RDX versus that at sort of any given point in time here. And we see by looking at the graphic, we do get isotopic enrichment. And when we actually regress this is what's called an epsilon value, or an isotope enrichment factor. And this is a method that you can use to determine how much enrichment you get as a compound degrades. And we see in this case for this organism, we get about what's called -10 per mil. That's a part per thousand measurement for nitrogen. So we get a nice enrichment in 15N in RDX, and we also get a measurable enrichment in C13. So if RDX is degrading in the field, in the laboratory, by this organism or under this set of conditions, you might expect to see isotopic enrichment as well. And if we move to the next slide then, and that's in fact what we did at the barrier, is we collected initial points before we installed the biobarrier, and then I showed you some data from June. We did a collection in June as well, and we ran stable isotope analysis of both carbon and nitrogen and RDX. I didn't show the October data, but essentially, everything was baseline. Now, when we did that in June, downgrading of the barrier and plotted those isotope ratios as a function of concentration, we see that we got isotopic enrichment for both nitrogen and carbon, and the ratios were reasonably similar to what we saw in the lab with different organisms that we looked at. So this basically shows that in the field you can use this technique to, again, further document degradation of RDX, and this can be particularly useful at a range environment where you might be trying to document natural attenuation, because clearly with the plume characteristics you get at these ranges, it's difficult to do sort of traditional natural attenuation assessments and look at things like concentration changes, because you get these sort of ghost plumes in different areas where you get high and low concentrations and they intermingle with each other. So then in conclusion, our passive barrier was effective for joint treatment of both perchlorate and explosives. We removed over 90% of RDX HMX for about a year. We had sustained pH control, so that the pH buffer worked well. We did see rebound at about 16 months, but I think a lot of this was due to excessive substrate demand. And you may need to re-amend this barrier periodically, but if it's installed properly, again, with sort of a trench type system, maybe with some lines, this could be something that can be easily done by range personnel, yearly, and it probably would take less than half a day. We didn't affect any, luckily, America's still safe. We didn't affect any mission critical activities. And I think the stable isotope analysis also provides really nice additional documentation of RDX degradation. And this is some fairly new work that's funded by ESTCP. And hopefully this approach will be applicable for groundwater on a variety of different DoD ranges. I'll conclude with that. You can get additional information at the link provided, or you're always welcome to give me a call or shoot me an email.
Great. Thank you so much, Paul. And just a reminder to everyone, you can download a copy of these slides. They're already available for download in PDF format on the CERT-up and ESTCP webinar webpage. and both the audio and the presentation will be archived on the web page and available for download in about a week. So we're going to go ahead, Paul, and start taking the questions we received for you. The first one is, Dr. Jenkins did not mention using multi-increment sampling to locate areas with perchlorate contamination. Is this approach applicable to your site?
I think probably Dr. Jenkins might be the person to answer that.
Tom, would you mind jumping in?
Yes, I'd say that if the contaminant is still located at the surface, it would work fine. However, perchlorate is so soluble that it can dissolve so rapidly out of the surface that if you didn't find it, it would not mean that there hadn't been perchlorate there and that it wasn't already in the groundwater. So that would be my concern.
Great, thank you. Paul, are explosive residues from low-order detonations a primary source of groundwater contamination on DoD ranges?
I'll yield to Tom also, but I think that is, when you have high-order detonations, there's very little explosive residues left typically. But with the low-order detonations, I think typically that's going to be a primary contributor to, these concentrations. And certainly if you go out and try and do a little site assessment on these ranges, you're going to find, and that's why Tom spent, so much time, trying to figure out how to do incremental sampling, because the distribution is so unusual based upon, where these in part where these low order detonations occur. So yeah, I believe it is a real major contributor. I don't know if you had anything to add to that, Tom.
No, I think comparing low order and high order, certainly the low order overwhelms the amount of residue deposited. The only other area that you do have to be concerned about are old dud rounds that over time corrode and leak. And there's some work being done on that, I think, by Susan Taylor at Corel, but it's not something that we dealt with in this particular project.
Great, thank you. Paul, did you do any testing to determine that the appropriate microorganisms were present before you injected your substrate?
Yeah, we actually did. We did quite a bit of testing in the laboratory. We looked at, we knew we wanted to use a slow release substrate, so we looked at some different formulations to try and see if, there was any preference. We knew that the organisms occurred naturally. We got very good degradation, but it was, was somewhat specific in terms of the oil formulation that we used. Again, we were also trying to figure out. We knew we had to buffer the aquifer, so we looked at a couple of different sort of potential buffering products as well. But yeah, the answer to that is yeah, we did upfront laboratory. We did both column and microcosm studies, and based upon that, we selected the amendments that we used in the field.
Great. And when you used the design tool you described, what life would it have projected for the amount of carbon added?
That's a good question. It's been a few years now. I'll have to go back and look. I'm sure we saved that. Part of the issue again I was having here was just the geology here is not. If you go and you're going to install a barrier, what you typically don't want to see is a big clay aquifer with a bunch of sand stringers. So it wasn't an ideal location, and as a result, it did kind of make the choice to reduce the oil concentration over what would have been predicted in the design tool. But I honestly don't recall what that would have been predicted, and I'm not sure whether the prediction would have been that great anyway, because again, this aquifer is dewatered for portions of the year, and I think that changes the kinetics dramatically of how quickly the oil gets consumed.
Great, thank you. Are the microbes that degrade perchlorate and RDX more or less ubiquitous?
Well, at most of the locations that we've looked, where we've done microcosm studies or column studies, it seems like you typically get perchlorate degraders just about everywhere, and the same thing for RDX. Now the substrates, we've had a couple of instances, and Picatinny Arsenal was a very interesting study we did where cheese whey happened to be a substrate that really dramatically promoted RDX and HMX degradation, and a lot of other things that we tried, including things like lactate and acetate and some sugar sources, actually weren't very effective. So the organisms were there, but there was some substrate specificity in terms of providing them with the carbon source or the electron donor that they needed to degrade the different contaminants. With perchlorate, again, these organisms tend to be very ubiquitous. There is, again, a bit of substrate selectivity, and also with perchlorate bugs, pH is a very significant issue. And we ran some studies years and years ago at Indian Head, which is a site which is not very far from Dahlgren. And the pH was quite low there, and over many months we didn't see any perchlorate degradation. We added a bit of buffer to the samples to bring the pH from 4 to 6, and within a week or two the perchlorate was gone. So the organisms were existing, but for one reason or another, and I'm not sure what the answer is, at those low pH conditions they didn't degrade perchlorate.
Great. You managed to answer 2 questions in one shot because there was a question specific to the buffering. Okay. In trying to extrapolate your work to closed ranges, have you looked at trying to saturate the entire range all at once to eliminate the need to install the wall every 2 years?
Well, interesting idea. I don't know logistically how easy that would be to do. I guess it's going to depend a lot on the site-specific characteristics. I mean, I could foresee a scenario where, particularly in high concentration areas, you might be able to, add enough of a dilute oil substrate that you could, saturate through. Again, in this type of site, you had a shallow vadose, so you could potentially get your substrate down into groundwater. So yeah, I mean, there could be, depending on site-specific conditions, the potential to use this at larger scale, maybe through surface application. In the instance with the active ranges or other ranges where you have, some flow paths that are moving off, I think still probably a barrier would be a little bit better approach, and particularly, a barrier that you could re-amend at some point in time. Great,
thanks. Can you tell us if these emulsified oil barriers, if they can be useful for other contaminants besides explosives and perchlorate?
Yeah, absolutely. Really, they were developed, emulsified oil was developed much more for chlorinated solvent degradation, and I think that's probably its most widespread application at this point. So it works extremely well as a barrier to promote degradation of chlorinated solvents. But I think it makes a nice substrate for lots of different contaminants that can be anaerobically degraded. Other things like nitrate would work very well. Anything that can be degraded reductively, it tends to be a pretty good substrate for that.
Great. Now some questions for both of you. Tom, starting with you, can you tell us about the potential next steps for the work? I know you're retired, but we're assuming that the work is being carried on. Are you aware of what next steps are being taken to further the state of knowledge in this area?
Well, as you know, I'm not participating in them, but I am aware of some work that's being done for CERTA. I think it's Jay Hathaway and Marianne Walsh. They're looking at sampling units that are not square. In other words, when we did our R&D work, the sampling units, we just used square sampling units because it was convenient for our approach. But a lot of sampling units are not going to be in that kind of configuration. And there's work being done by them to establish a good way to get incremental samples in various shaped sampling units and that work I think is ongoing right now. And there's going to be a tool, apparently it's going to be available through the visual sampling plan work at Patel Lab, Research Pacific Northwest Laboratory. And that's going to be apparently available pretty soon. So that's what I am aware of. I think there's been a lot more work done in conjunction with residue deposition by Mike Walsh. They've done work with DNAB and NTO. These are types of explosives that the Army is looking at and other agencies are looking at to replace TNT and RDX in the future. And so they've been looking at deposition and analytical methods, et cetera, for those contaminants as well.
Thank you. And Paul, for your work, what are the next steps, and how can you direct some of the end users on the call to current and future resources?
Well, Rula, I think we're still spending a good deal of effort developing the CSIA method, and that method, should be commercially available through Neil Sturcio at the University of Delaware. But we're trying to understand, biological degradation. We're trying to calculate these different, what they're called fractionation factors with different types of organisms. So to see if we can distinguish, if RDX is degrading by different pathways, do we see different isotopic fractionation? We're going to continue to do field work, including we're planning a summer push-pull test at the Dahlgren site, where we're going to go down and at the emulsified oil barrier, add a little RDX to the barrier, and then pull samples back, and once again, look at isotopic fractionation and compare that to what we saw with the sort of initial round of testing we did in the field. We've also worked with Mandy Michelson on another ESTCP project where actually aerobic RDX degraders were injected into a site in Umatilla, Oregon, and we collected subsamples there to try and see if we can document RDX degradation by aerobic bacteria, if that's occurring. That remains, again, sort of a question that's important is people in the laboratory have isolated aerobic organisms that degrade RDX, but it's very difficult to see evidence of that occurring in the field. And in many instances, when we set up aerobic microcosms, we don't see any evidence of RDX degradation. But perhaps we're missing something. So having an isotope method where you could go sample if you see isotopic enrichment, that could be very important. And then we're going to continue, at least on this project, through the end of the year. We plan on 1 or 2 more sampling events to see, now that we've added a more concentrated oil solution, do we get a return to low concentrations of RDX and perchlorate? And again, sort of take a look at barrier longevity. And then, at the end, we'll talk to the range environmental personnel about and just make recommendations concerning, implementation at a larger scale to prevent off-site migration from that range and others that they may have locally.
Thank you so much, Paul. And Tom, as we get ready to close here, can you re-articulate your key take-home message in 60 seconds or less, particularly from an end-user perspective?
Okay, I guess in quick summary, the largest contributor to contamination on ranges is lower detonations. The contaminants are distributed non-homogeneously across the site. Trying to collect a sample to estimate the mean using a discrete sample doesn't work. The multi-increment sampling approach provides an excellent approach to collect samples that you get a good estimate of the mean concentration. But you must use that in conjunction with sample grinding in the laboratory. Otherwise, you lose the representativeness that you gained in the field. And once that's done, if you use one of the SW846 EPA methods for that, method 8230B, either with HPLC UV or HPLC mass spec, you'll get a good estimate and get a good reliable result for the sampling unit of interest.
Thank you so much. And Paul?
Sure, Rula. Sort of in conclusion, you tend to see commingled contaminants on different DoD ranges. These include nitramines, also nitroaromatics like TNT, which this barrier would also be effective for, presumably, although there was none in the groundwater here. You need some type of approach to treat those contaminants in groundwater that's not intrusive to range activities, so you need something passive. And one option is an emulsified oil barrier. It was very effective. It may be something that you have to, make engineering design such that you can re-amend the barrier at some point in time, if you plan on running this over many years or decades. And there's also some CSIA methods being developed that could be very useful for documenting both natural attenuation of RDX as well as degradation in a design system such as this or other systems that are used to try and treat explosives in groundwater.
Wonderful. Well, thank you both for excellent presentations and for answering the questions so well. This concludes today's webcast. Our next webinar will be on June 25th, and it will focus on the weapons systems and platforms program area, and the topic will be energetics, colored smoke, and flares. If you please can take a moment to complete the survey that will pop up on your screen when the webinar ends, we would really appreciate it because it helps us plan better for the future. So on behalf of CERDP and ESTCP, thank you all for joining us, and we hope to get you on the next webinar.